Alright everyone, so welcome back. This is chapter 53. This chapter is all about population ecology. So how do we study population size versus dispersion? And the chunk of this chapter really focuses on population growth and the factors that determine how those populations will in fact grow. So let's just start off by remembering a couple of things. First off, we talk about populations, we're talking about a group of individuals of the same species that live in the same general area. And that definition is very important. Both here, it's going to come up again in evolution. And the big thing is to keep your definition for population separate from your communities. Big difference. Communities are a bunch of species in the same area, your populations are a single one. We typically study populations based on their size, boundaries, as well as their growth. And that's really what this whole chapter is going to encompass. So population ecology in and of itself is studying these populations in relation to their environment. So we include everything from population density to their distribution. We'll look at some demographics that both overlie human population growth as well as other organisms out in your typical ecosystems. And age structure kind of falls into some of that, as well as your population size in and of itself. So, population density. We're looking at the number of individuals given some sort of defined unit of either area if we're talking a terrestrial ecosystem or volume if you're talking something aquatic. And this is really a dynamic situation. So you're going to have all sorts of factors that affect your population density, and that's going to be factors that add new individuals to your area. So immigration, individuals moving in from another area, as well as your birth or your natality rates, literally adding new individuals, not just to the population, but to Earth in general. All right. That's sort of fluxing in, and then the movement out, you've got your death or your mortality rates, as well as your emigration, where those individuals are moving out of the population. So if we take a look at sort of just a really basic idea, that immigration is going to add individuals, the natality, that birth rate is going to add individuals, while your mortality rate and your emigration rates are going to remove them. So it's a flux. You're going to have individuals moving in while individuals are dying, and having individuals being born while you've got emigration going on. So when we talk about population density, you're really talking about a moment in time. And that density can change from one moment in time to another, and that's when we can start talking about population growth or even decrease, and what does that look like over time. So one of the things we've got to keep in mind is when we're talking about calculating population size in a given area to determine our density, it's not really practical to count every individual in that population. All right, and in some cases, not only is it impractical, it's just downright impossible. So we've got to have sampling techniques that we can use to estimate those densities, to estimate those population sizes. And a couple of ways we can do that, we can take small samples and we can kind of quadrant out sizes within our given area and take those samples and sort of extrapolate from there. So if I've got 10 individuals in this particular area and I cordoned off 10 of those, I can say, well, 10 times 10, there must be approximately, here's my total. All right. We can also use indexes. So that extrapolation works particularly well with things like plant species and trees and shrubs, things that don't typically get up and move on us. So it's a lot easier to take that sample. Where if you've got organisms who are moving, all right, your birds, mammals, reptiles for that matter, sometimes it's more practical to take a look at sort of these indexes, such as your nests. All right, I can go count the number of nests in a particular spot in the forest, and then I can even use that then to extrapolate up. So a lot of these get used in conjunction with each other as well. And then there's your marker capture method, where here we're going to take a certain number of individuals, we're going to capture them, we're literally going to take them in and tag them. In some cases, that tagging might literally be something like a radio tag, where we're going to put it on, say, a deer population and re-release them. A lot of times with insects, they'll do it with little bits of nail polish or some sort of ink or dye so that we can find them again. But the point is to tag them so that we know whether or not we've seen them before. So, random sample of individuals, we capture them, we tag them, we re-release them. All right. And then over a certain period of time, we're going to go back and recapture a second set of samples. We're then going to take note, all right, I captured 100 individuals the first time, I released them after I tagged them, and now when I recapture another 100, I got 50 of them back that I had already seen, and now I have a new set of 50. So we can utilize the formula where we denote S being the number of that original sample, N being the number of new samples that we see, over X, which is how many we got in that second sample that had already been marked. All right, and that sort of simplistic mathematical formula there down in the corner gives us an idea, an estimate for our population size. All right, and the big thing is a lot of this is estimation. We're not really going to know the true number just because it's not practical. We don't go out and count every individual, or at least we attempt to anyway, in the US. We do a census. All right, and so we're relying on people to send that information back, but we certainly don't know every individual in the country. All right, so that's sort of the point here. Not only can we talk about just the sheer number of individuals in an area, but we can also start to take a look at how do they disperse themselves within that area. And that's where these dispersion patterns, these spacing of individuals, becomes kind of interesting because, all right, it's great we know that there's 100,000 particular wildflowers growing in this area, but how do they space themselves out? Or there's 50 wolves in this corner of Yellowstone, but how do they sort of space themselves out? All right, and that starts to give us some indications as to their behaviors, particularly with the mammals. So we've got three potential options. They can be clumped together, which if you take a look at the picture here, that's what you're looking at right here. All right, and these individuals are going to sort of aggregate or literally clump together, and this sort of dispersion pattern tends to be found in one of two instances. Either they're clumping together because of resources, so they need to clump around the water or the availability of particular food sources. But a lot of it also comes from behaviors. So for the wolves that they show there in the picture, they live in groups because it increases their ability to hunt. All right, so they hunt in packs. Uniform, these guys are completely spread out, so that's what we're taking a look at right here. And this typically comes up because of territory. So they're spacing themselves out because I need this much territory and I'm going to defend that and you're not going to be able to come into it. And so they're going to spread themselves out that way. We see a lot of that in that particular situation. And then you've got just the complete random, come what may, this is where I fall. And we see a lot more of that in our plants because they're not able to kind of get up and move and have much influence. It's sort of wherever their seed falls, that's where they sprout. But we can see it in other organisms too, where there just isn't as much of a attraction or repulsion for one form or another. Okay, so that's the idea there.